Hey everyone, welcome to the second half of our quadratic equations and graphs of parabolas topic. Now we are finally going to get into talking about the parabola and what this actually is. Now before I give you any of the maths terminology or any of that, you have actually seen these parabolas probably a lot more than you may realize. Now, I'm going to give you a series of kind of images or day-to-day things we could have come in contact with that will give you a sense for a type of recurring pattern or a recurring shape. Now, take for example a water fountain. So when you spray the water out, what kind of motion does it make? Well, it shoots out of the fountain. And I mean, you'd probably be up here drinking it, but if you were to just spray a water fountain, it's going to make this type of arch shape. Now, if any of you have been to San Francisco in the US, you can even look this up on Google Images. You can look up the Golden Gate Bridge. Now, this particular bridge, I'm going to draw a very dodgy kind of design of it here. Let's make this smaller actually. If we, for example, have this bridge here, and we have the road down here, and it has this archy type of pattern happening here, connecting the top of each of these little pillars here. And I don't know, think back to maybe throughout history, if you've ever heard of or seen a picture of a cannon being fired. So these cannons, they would fire these balls come out of the cannon, and they go through a type of motion, right? They shoot out from here. They come up, they drop down, and you have that. Now, this and any similar projectiles to this all follow this similar pattern. Think about people, if you're a sports fan, people shooting a basketball. Now, if you've ever played basketball, you will stand here, you've got the ball in your hands, and when you shoot it, you have your hoop up here. You have this hoop here. This is a very bad drawing, but you're not going to want to throw the ball just kind of like this, very flat. You want a type of arch to your shot. So when you shoot it, you want it to kind of go above the rim and then drop down. So if we look at all of these images, they have something in common. So we have the water fountain, or we call this a bubbler in Australia where I'm from. We have the Golden Gate Bridge. We have a cannon being fired and a basketball shot. Now, you can even try to simulate one of these. If you scrunch up a bit of paper and throw it in a bin, something similar to a basketball shot, have a look at the type of, if you try to follow the trajectory, how the piece of paper will fly up and fall, you will see a lot of these peculiar shapes, and we see these shapes every day in nature without realizing. Now, these things are examples of parabolas. So we've got the water fountain here. It has this type of arching thing, which kind of looks similar to the cannon or the basketball shot. Or going the other way, the Golden Gate Bridge, for example, starts at the top and then goes down, comes back up again. all of these things are examples of what we call a parabola. Now let's look at some of the features of these particular things, because this video is just an introduction to these, kind of like a soft introduction, so you don't get too overwhelmed, because this topic gets a bit harder quite quickly. But just for now, let's look at these two types of parabolas that we have just drawn out, that we see in nature. So what kind of similarities do we notice about both of these guys? So if we compare this first one on the left, we see that we start down the bottom and our thing goes up to some kind of maximum point. So this maximum point as well is where this thing turns. So in the one on the left, we can see we have a maximum point, a maximum height this increases. When you shoot a basketball, for example, it's going to hit this kind of maximum point up here before it drops back down. Now, we call this thing a maximum turning point. So, by turning point, we just mean the point right at the top where we get this curve, where our parabola begins to change direction. See how here it's going up, and right at the top here, it turns, so it goes back down. Think of a basketball shot, think of a cannon being fired. They all have this type of motion associated with them. Now, what else do we notice here? Well, we have, at this maximum turning point, if we say drew a vertical line through here, you can see now, once we start dealing with some proper parabolas, when I get some nice drawings in, you'll be able to see this a bit clearer. But at this maximum turning point, we actually have an axis of symmetry. So that means that right at this top point, this is reflected on the other side. Hopefully you can see that here still with my bad drawing, but we have an axis of symmetry here. And we also get that with this guy. If a better drawing was given, we get an axis of symmetry for both types of parabolas. We get one for this one as well as this one here. Now, we've talked a lot about this one on the left. Let's switch gears to the one on the right quickly, because we can see that this is kind of the opposite thing happening. So what's happening here is we're starting here. We started on the bottom and finished on the bottom, and we went up, landed at a max, and then went back down. Whereas for this one here, we start at the top, go down to a minimum, and come back up to the top as well. Think about the Golden Gate Bridge. We have these two big bits on the left and right, and the wiring joining them starts at the top, goes down to a minimum, kind of down here, and then shoots back up to the top of this next one. So, for these, we can say that, say down here, this is what we call a minimum turning point. And these two guys here are the two types of parabolas we're going to be dealing with. Now, these guys have a particular name. So the one on the left here, we call this one, and we'll talk about this a lot more in the future. This one is what we call a concave down parabola. And this one on the right is what we call a concave up parabola. A good way to distinguish between the two is, if you look at this one on the left, if you look at the shape of this kind of looks like a sad face. And when you're down, like, so if I drew kind of a couple of eyes here, this looks like a sad face here. Now, when you're feeling down, you're feeling sad. So that's a little way, maybe it may help you remember it, maybe not. Or if you're feeling up, if you're feeling really happy, you are going to have a big smile on your face. So a concave up, when you're feeling up, it looks like a smiley face, a kind of positive smiley face. This one is a negative kind of sad face. So hence distinguishing between the down and up. That's just a little thing I use. If that just sounds completely preposterous to you, don't worry about it. You don't need to use that. You can remember it in whatever way you'd like. But these are some features to these particular parabolas that we see in everyday life. Now, applying this to maths, we are going to be working within our XY plane, like we did with our linear relationships before. So when we graph these parabolas, this is where our quadratic equations come in. So all parabolas have what we call the standard form of this particular thing here. Now, this right hand side you may recognize from quadratic expressions, but this is the general form of all of these parabola graphs when we start sketching these here. Now, what we're going to do for this first example, we are going to look at the simplest quadratic expression we can. So this is what we're going to look at is if my B and C coefficients were 0. So the particular one I'm looking at, and if A was 1, is my graph, which I'm going to drop, of my parabola y equals x squared. I hope we can all agree this is, compared to some of the quadratic expressions we were doing before, this is the easiest one we can work with. And we're going to be coming back to this one quite a bit. Now, if I drew a couple of markings here, and we actually went in and drew the parabola, well, drew this particular relationship using a table of values, we're going to see something very interesting coming up. So think back to linear relationships. When we wanted to draw some kind of linear relationship, we plugged in a couple of values into what we called a table of values. So we looked at different values of x, and we saw what would get spat out with the y value once we put that into the equation up here. So if we substitute x equals -2 into the equation, we get that my value for y is going to be -2 all squared. So that's going to give me 4. If I put in -1 in place of the x, I get y equals to -1 all squared. This is 1. And if I have 0, 0 squared gives me 0, 1 squared gives me 1, 2 squared gives me 4. Now we're going to plot all of these points here on my graph. So when x is -2, my y equals 4. When my x equals -1, my y equals 1, positive 1. When my x equals 0, my y equals 0. When my x equals 1, my y equals 1. And finally, when my x equals 2, my y equals 4. So these are all my points. And if I were to connect these dots, we can already kind of see this isn't going to be a linear relation. It looks like my thing is curving. So if I drew something going all the way through these points, I'm going to get a type of sloping parabola. And this is a concave up one. This is one of these guys. This is our Golden Gate Bridge example from the introduction. Now, this is how we can think about sketching these types of parabolas. Now, let's actually look at this particular parabola, and we're going to notice a couple of things. Well, if we were to ask ourselves a couple of questions. What if we, first, let's kind of state the type of parabola. Parabola. So we said before that this one is the kind of smiley face parabola. So this is going to be a concave up parabola. So this is concave up. Another question we're going to ask ourselves is, where is the axis of symmetry? And what is this middle point here that acts as an axis of symmetry? And what is the equation of it? Well, I can see here, this side looks like it's reflected perfectly over here. So the middle of that, this axis of symmetry, is going to be right down the middle here. Now, what is the equation of this particular line? Well, this is a vertical line. Now, if we have these vertical and horizontal lines, they have a very unique equation. Now, for this one here, my vertical line, it's always going through an x value of 0. So my axis of symmetry, the equation of my axis of symmetry is going to be x equals 0. And similar to when we worked through linear relationships, what are my intercepts? Now remember, we have x and y intercepts for linear relationships, and we also have the same for these, what we call non-linear relationships, things like quadratics and parabolas. Now here, in both cases, the x and y intercept is going to be 0, because along the y-axis, it cuts through at 0, and for the x-axis, it also cuts through at 0. So my x and y intercepts are also going to be 0. Now, let's look at one more feature here of a feature question for these parabolas. Now, I'm going to draw up a graph very quickly. And it's not going to be very nice, so please just bear with me. Okay. For this particular parabola, and I'm not putting in any of the other markings because they're not super time efficient. But I want to identify all of these key features that we talked about before. So when we bring our parabolas to the x and y plane, we start considering some of the same features that we learned in linear relationships. So first of all, we want to find the turning point and what type of parabola this is. So we can see that it starts at the bottom, goes up to a maximum, and goes down. So this is a parabola which is concave down. It is this sad face type of parabola. You feel down when you are sad. So our type of parabola here is concave down. Now, I just forgot to put a point in here. Now, what is the turning point? Let's do that for question B. Well, first we want to identify what is the maximum point on this parabola. Now that is up here. So this is concave down, so we know that there is going to be a maximum turning point. And we want to find the coordinates of this. So if we draw down to the x-axis here and across to the y-axis, we can get the coordinates of this turning point. So in our coordinate system, our x always comes first. So I'm going to have a -3 here because it stretches down to x equals -3. And my y is going to be 5 here. Now for part C, let's take this thing and look at what the axis of symmetry is and what the equation of the axis of symmetry is. So some of you may have noticed that this particular vertical line is actually the axis of symmetry, because if you look on the left, what's happening on the left is reflected on the right, has this mirroring effect. So we want to identify where along the x-axis does this axis of symmetry fall, and that is at this -3 point. So this horizontal line that we draw through, this guy here, that stretches on and up here and down here, its equation is x equals -3. This is, once again, just all revision from linear relationships, these types of horizontal and vertical lines. Please consult those videos if this is a bit confusing. But our equation of our axis of symmetry is going to be x equals -3. And finally, we want to find the y-intercept. Now, going back to linear relationships, we defined the y-intercept as the point where the line or graph passes through the y-axis. Now, that we can see is down here. It's passing through this y-axis down at the point of -2. So my y-intercept is -2 for my y-intercept. And what's my x-intercept going to be? Well, in the previous example, we saw a parabola that just had one x-intercept at 0. But what about here? We notice we have 1 and 2 x-intercepts. So this is, in essence, a different type of parabola because it has 2 intercepts as opposed to 1. Now, this idea we are going to talk about a lot in the next few videos, so just keep it in your mind. Don't dwell on it too much because we are going to cover this idea a lot in future videos. So my x-intercepts are, here we can see -5 and -1. So we have now moved on to identifying all of the key features, and that's where we'll end it today. So just to recap, all parabolas have typically some type of intercepts, whether that be x-intercepts or y-intercepts, and we'll see a bunch of different cases of these. They all have an axis of symmetry, and they can be classified in 2 different ways. They can be either concave up or concave down. And when we have these concave down ones, for example, we have our maximum turning point, a top bit before we go back down. Think the basketball shot, think of the cannon, think about a water fountain or a bubbler if you're from Australia. And the minimum ones the minimum turning points belong to the concave up parabolas. So thinking about our Golden Gate Bridge example, we're going to have some kind of minimum point where we turn and go back up. So that is some examples of some parabolas we see in everyday life, as well as how we can think of translating these parabolas into the X and Y plane. Thank you so much for joining me in this video, and I'll see you next time.